Welcome back, everybody. I would like to come back to the first question that was asked before the break, because I realized I'm not sure if I answered it really fully. Let's come back to it. So you were asking what should be an acceptable difference between the worst and the best, or between the worst and worst of the best. If I have to quantify, what I would say is a factor of 2 is acceptable, right? It's still okay, right? You will still have twice the amount of time and so on. So up to a factor of 2 is okay. What's going to typically happen, however, is that when it happens, it's not just going to be a factor of 2 or 3, it's going to be a factor of 10 or 100. It's like one of the slots just gets stuck for forever. It's like you go to the supermarket and you are at the cashier desk queuing, and then you try to go to the shorter queue and so on, and then it just gets stuck forever. That's just the Murphy's Law in real life. And in that case, this is really what happens, is that when it happens big time. Like the slot is really completely stuck for an hour. Does it answer your question?
Yes, thanks.
All right, perfect. And of course, this is the sort of things that happens when you have 1,000 machines, right? If you just have a few machines, it's very unlikely. But if you have 1,000 machines, it's almost guaranteed that one of them is going to have the problem. All right. Okay. Let's continue then. So let's close that part. Again, I hope I didn't scare you too much, because maybe it was a bit technical or going more in depth. Usually it's really for the computer scientists. So I still threw it at you thinking that it can be interesting for you to understand, but do not worry, of course, if it went a bit too far technically. It's just the intuition that I wanted to share with you. Let's go back now to some practical and popular products. Document stores. So document stores is also sometimes referred to as NoSQL. At some point, it was even a buzzword. I don't know if it still is today, but it was a buzzword. It's kind of contrasted to SQL. It's the idea that we relax everything. We don't need a schema. We denormalize and so on. It was a bit this revolution. Some people thought that this is no in sense of we don't want SQL at all, but actually it should be interpreted as not only SQL. The idea that there are also alternatives to SQL for the case that the data is not fully normalized or fully structured. So what happens is that we built this structure stack. It's already 50 years old now. It dates back to the 1970s. Where you see that we have tables that we can query. These tables have a relational schema, which means we have columns that have types. We can store them as well-formed CSV, the comma-separated values. Then CSV is then text, and text is encoded to bits. And then you can store these bits on somewhere, right? Of course, as you can imagine, the real database management system, they are not going to do CSV, right? Because CSV would be inefficient. They, of course, use more binary formats, a bit like Parquet and so on, to store it more efficiently. But it is the essence of it, right? In a data lake, you could have CSV files that you query and so on. But this is more or less the stack that there is, even though you can take shortcuts at a few places, right? So the tables, you remember, we did it in the first week of the lecture, right? It has rows and columns, and basically everything is a table. Then we looked into the relational integrity, the idea that we have the same columns everywhere, the atomic integrity, the idea that we don't have tables in tables and so on. Then we had schemas. The schemas is when you say, okay, everything in that column is a string, everything here is an integer, everything here is just 3 charts. That's probably airport codes. We love to have airport codes when we teach databases in universities somehow. And the date in that column. So that means that we have, in addition, the domain integrity when you have this. By the way, I realize this is a typo here. It's the same here. I just call it relational integrity. It's the same thing that I mean. Tabular integrity is just the same thing as relational integrity. So this is just the third constraint that comes from the schema right there. All right, so you see it's the beautiful world of structured data where you have these 3 integrity constraints fulfilled. And in this beautiful world of relational data, you have the relational algebra where you can project to some columns, you can select a few rows, you can join tables together, you can group and aggregate your data, you can sort your data in any order you want. So that's the beautiful world of the relational algebra. We have the syntax, as I explained to you. There's the physical view with the actual way you store it. Business people love to store it that way. CSV files, you can download them from the internet, open them in your favorite spreadsheet software, and start running your analytics in Excel. But the logical view is going to be a table, right? No matter what the syntax is actually going to be. All right. And then we have a language, the language known as SQL, that is 50 years old, undisputed, very popular. I don't think that anybody else would even think of a different language for tables than SQL. People would think of alternate technologies like pandas, data frames, and so on, right? But they would not dispute the language SQL. They might decide not to use it, but they are not going to decide to use another language for tables. There's basically only SQL out there for this use case. All right. So that makes it easy to learn because you just need to learn SQL, and that's it if you want to query tables. It's universal. So you see this select from where, having, order by, limit of set, group by, and so on and so on. You know, see this whole set of clauses. I think I didn't say it in the right order because there is an order to the clauses, but you got the idea, right? So there are all of these clauses that you put, and then you can transform tables into tables. All right, and so there is this whole stack that used to be monolithic back then in the 70s. And now we are rebuilding it for the big data. So in fact, as far as tables are concerned, we are almost done. Actually, we have pretty much everything, right? We can store in a data lake if we want, right? It's not necessarily the fastest, but you could store CSV files in some encoding. It's UTF-8 is the most popular way to encode text into bits on a hard drive. And you use AGFS for storing it. Then you open them as data frames. You know, you can open a CSV file as a data frame in Spark. Then you can use Spark transformations. You can even, if you prefer, use HBase as your data store, right? And then you can use SQL. There are actually SQL implementations on top of data frames. It's called Spark SQL, right? So in other words, you could use Spark SQL to query your data seen as a data frame right from HBase, or right from HDFS as CSV. So you see it's modular. You can just do whatever you want and combine all of these things in any way you want. All right, but we've pretty much done almost everything in there in the data stack. But as far as denormalized data or trees are concerned, so XML and JSON, we are not done, right? Because as far as XML and JSON are concerned, we don't have that part right there. So this is the missing part, and that's going to keep us busy for the rest of the lecture. So if I look at now specifically collections of trees, XML and JSON, well, I can still use my data lake, HDFS, S3, Azure Blob Storage. I can still use this encoding. Now I'm going to use XML or JSON probably as a syntax there. I'm going to view them as trees and not tables in the data models. So collections of trees are just denormalized tables. I can validate with XML schema, with JSON schema, with JSON, and so on and so on. If I validate JSON, it gives me even data frames. That's great because data frames actually support trees if there is a schema. And then I can use Spark on top of that. I can even use Spark data frames on top of that if I actually use a data frame to open my JSON file. This is going to work if there is a structure in my JSON files and all of my JSON objects, and all of my JSON objects kind of are valid against the same schema. Then I get a data frame. But then I told you can even do better than that and use Spark instead to store it on HDFS. We have a question.
What is the difference between Nosql and Spark SQL? Both deal with heterogeneous data, right?
Spark SQL is the name of a technology. It's the name of the SQL dialect that is implemented in Spark, right? So Spark SQL is a language. NoSQL is not a language. NoSQL is more like, let's say, a community or a movement in the database community that is called NoSQL. But it's really just a label for all of these technologies. It's a label for MongoDB, data lakes, you know, and I think you could consider, if you push it a bit, you could consider that because Spark SQL supports nestedness via arrays and so on, you could consider that Spark SQL is a bit within NoSQL as well. Right? It's kind of in between SQL and NoSQL. You could absolutely say that, right? But the important part is Spark SQL is a real language that is implemented. NoSQL is just the name of a scientific movement in the database community, right? Just like big data, actually, big data is also like that. Big data is just you know, a buzzword, and NoSQL is also a buzzword. Okay, and the problem, of course, with buzzwords is that people can understand them in different ways. So this is the reason why I cannot tell you exactly, because people might not have exactly the same understanding of NoSQL. It's a matter of perspective, right? Okay. All right. So basically here, I just repeated things we've been doing, right? There was nothing new in what I was saying, right? But basically now you have all of these technologies that you learned, and you can query your data in plenty of different ways. So you can query directly from JSON. Maybe it's going to be slow. Then you just validate your JSON, store it back as a Parquet file, and then you read it again as a data frame with Spark, then it's faster, right? Now you know how to do all of that. You know exactly how to do it. But I still owe you that part right there, because that we haven't done. And as you noticed, if you actually do query a JSON or Parquet with Spark, or Spark SQL, it is actually going to be cumbersome. It is going to be cumbersome. So there's better ways. So in the semi-structured stack, so when you look at NoSQL, or XML and JSON are also part of NoSQL. You could consider that XML and JSON are also NoSQL. What happens is that it's possible to skip the validation part. For tables, you need a schema. You have no other choice. You need a schema if you want to define a table in your system. But in XML and JSON and in the document stores, as we will see, you do not have to have a schema. You can actually create a collection of trees on the logical level without a schema. And you just drop JSON objects in there, you drop XML documents in there. All you care about is that your documents are well-formed, XML or JSON. Right? However, there is still the option to validate. Right? If you want, you can validate your data and turn it into data frame if it was JSON and so on. But you don't have to. It's a freedom. It's an extra freedom that you have. And this is what NoSQL gives you, right? Not only SQL. You can also skip the validation. That's the one message in there. But what I want you to understand is people have spent a lot of time trying to fit the trees into tables, because they didn't want to invent new technologies. They said, okay, we already have relational tables. Can we just not fit the trees into these tables and just use relational database systems, right? People tried. And actually, if you start looking at it on simple example, it makes a lot of sense to do that, right? Because for example, if you have this JSON object here, then you can instantly turn it into a table row. The same with XML, right? If you have this XML, you can turn it into a table row. And then if you have two, in that case, it's XML, two XML documents, then you get this table with two rows. It's a very natural thing to do, actually, right? You can then also map XML schemas like this that specify elements with types. You can turn this into a relational schema very easily, right? Like foo is an integer, okay, foo is an integer, bar is a string, bar is a string. So it looks like it's easy, right? So we can just turn everything back into relational tables and relational schemas, right? Like this is JSON again, and I can turn it into a relational schema. The problem is that it works until it doesn't. Because the example I showed you here are extremely simple. That's the case where your data is very flat. It's actually in the first normal form. You have types, it's predictable, and so on. The problem is that in that case, then of course you should be using SQL. What are you doing with JSON or XML if your data is flat and structured? There is no reason why you're using JSON or XML. You should be using tables. The problem is that there is a reason why people are using JSON and XML. And that reason is a double reason. The first reason, I'm repeating things all over here, but I make sure you understand that. The first reason is that you can have nestedness, arrays in objects in arrays in object, and that doesn't fit into tables. And the second reason is heterogeneity, is that the types might be different in every object, right? So the objects might just not look alike, but that's heterogeneity. And you can still try to make it fit into tables, right? For example, if you have this nestedness right there, you could try to implement it, like normalize it, and then do two tables that are joined together to basically model the same data. So Of course, if you do it on a case-by-case basis on every single data set, you will find a way to find an equivalent tabular representation in many cases. If it's heterogeneous, you can as well. Then you just have nulls in there, right? If you have missing fields, here there's missing last name, here there's a missing profession, that's okay. Just put nulls here, right? So you can make it work, basically. It will work. But the problem is that as you try to expand and generalize to any JSON object or any XML object, you're actually just trying to put a square peg into a round hole and hitting it with a hammer. And trying to make trees fit into tables is really this. This is what people are doing. It will just not work in the general case. So once people tried it and tried it and tried it, and they just realize it simply doesn't work in the general case where the data can be very nested and very heterogeneous, okay, then some people accepted it and said, we need new technologies. We just need to come up with new technologies, just like there's relational databases for tables. Let's invent something similar, but for collections of trees, right? And this is how the document stores were born. It's just a completely new bootstrap. We just do it all over again, starting from scratch. But this time, from day one, this is designed for collections of trees. This is called a document store. So in a document store, we don't have relational tables. What we have is documents. Millions to billions of documents. Of course, it's a big data lecture, right? So millions or billions or trillions of documents in a collection, right? It can go to terabytes, petabytes, and so on in a document store. What's very important is that the notion of document store doesn't care if it's XML or if it's JSON. Both of them work just fine. Actually, I know that people would scream if I say that, but JSON and XML is pretty much the same thing, right? It's just trees. So who cares if it's JSON or XML? So you will have document stores that are XML document stores, and you will have document stores that are JSON document stores, and everybody's happy, right? Now, there is one thing that XML does that JSON can't. This is for actual papers or publications where you need to tag text. That's the one case where XML is actually better. But apart from that, for data, they are basically the same. Right? And by the way, some people say XML is inefficient. Of course, but XML will also be stored efficiently. You can also find formats like Parquet or something to efficiently store an XML document. Of course, it doesn't have to be an XML text. So it's just a notion of data modeling. All right, so in a document store, now I'm going to JSON. I'm saving you the XML parts. There's plenty of very nice XML document stores, but I'm going to focus on JSON now, as an example, because it's very similar. So we have a collection of trees. In that case, it's a collection of 3 trees, this tree, and this tree. And you notice it's nested, it's heterogeneous, and because I have missing fields here and so on and so on. All right. So typically, the one thing to realize, because this is something, if nobody tells you, you cannot guess. When we have a collection of trees, it's going to be a huge collection of small trees. That's very important, a huge collection of small trees. It's exactly like, it shouldn't surprise you given what we've done before. We can have billions or trillions of small objects, right? So each document is going to be small. What do I mean with small? Very often it's a few kilobytes. It can also go to the megabytes. You can go to the megabyte. The main reason why you would go to megabytes is maybe you store an image in some way in there. So you could have megabytes, but it's not going to be more than megabytes. You are never going to have a gigabyte in a single document. So at most a few megabytes, but we have a lot of them, right? So thousands, millions, billions, even trillions, if you want, of such documents. Okay, so I repeat, a huge collection of small trees. The analogy with relational tables is that just like a table is a collection of rows, here we have collections of trees. And just like a table has maybe a very high number of rows, it can have billions or millions of rows, but the columns, there are not so many of them. So each row in a relational table is also small, right? Maybe you have 10, 20 columns up to 255, but that's pretty much it, right? So you scale in the rows, not in the columns, right? Even though, just to be complete, in HBase, we saw that we can also have millions of columns. Yes, but this is sparse. Most of them are empty when we do that. Okay, so huge collections of small trees. Okay, so again, you need to contrast a tree versus the flat case. And you need to realize that this is a special case when the tree is flat, that it actually corresponds to a table row. And the other aspect of this huge collection of small trees is that it can be a heterogeneous collection of small trees. You can fit all of these trees in a document store that works perfectly well. And optionally, if you want, you can also have a homogeneous collection of trees. And this is the case where you validated them against the same schema. But the difference is it's optional. You don't have to, and this is fine too. Okay. Another aspect of document stores, at least in their early design, is that they do a few things very efficiently. You can project, you can select, and you can aggregate very efficiently. The one thing that document stores typically will not do well is joining. Right? Joining, they are not good at that. So sometimes they do not even join at all. If you want to join, you just need to do it yourself in C++ or Java. They basically threw it at you. You want to join? Fine, okay, but we won't do it. That's your problem. Right? But you shouldn't be surprised by that, because we know that joins are expensive, and we know that joins can be avoided by denormalizing data. And it turns out that we have denormalized data. So how do you avoid the join? You just denormalize your data by nesting the data instead, and then you don't need the join anymore, right? At least in many cases. All right. So we'll see that that's why there will be another lecture after that when we actually bring back the joins. It's a good idea for many cases, but very quickly people realize that they actually were missing the join. And so everybody re-implementing the joins themselves in C++ and Java, and that's just a waste of resources, because you know, in a relational database, you just implement it once in the system and then people use it. But basically that forced people to just implement their join algorithms themselves. And of course, it's not done as well as it would be if it were in the actual original system, right? But anyway, this week we're going to live without joins. We just project, select, aggregate, and that's it. And there is no join at all. You basically need to do it yourself. Okay. Another factor, I know I'm repeating myself, but that way I make sure you remember. The validation can be done after the data was populated. It means that you can pour your data in your collection, and after that, you can say, okay, this is valid, this is invalid, right? And if it's invalid, you can still fix it, you know, update it, fix it, clean it up, whatever you want, right? For example, the reason here could be, I don't know why, yeah, maybe you say foobar must be a Boolean, and here foobar is 3, bad luck. It's just invalid, right? But this is fine, because in NoSQL, we have this flexibility. That would never happen in a relational database, right? But in NoSQL, we can. All right. As you can imagine, there are a lot of NoSQL document stores out there, a lot of them. So I put a few names right there, right? So ExistDB is an XML one. MarkLogic also started with XML. BaseX is also XML. MongoDB is JSON. Elasticsearch is JSON. Couchbase is JSON. This is also JSON here. I think it's also JSON, probably Cosmos DB. I have in mind they also have DocumentDB. But basically, you see there's a balance between XML and JSON, and they just cohabit nicely, right? Some of these companies are billion-dollar companies, right? So this is just to say there is a business with NoSQL and with these things, all right? And for this lecture, I'm picking MongoDB. I'm just picking it because it's quite popular, but the main reason is that first I need to pick one to teach it to you, right? But if you learn this one, you will see that it's very easy to learn the others, because again, they all work the same. They have more or less the same APIs. You know, they work in more or less the same ways, right? So this is why we'll focus on MongoDB as an example. All right, let me check the time. We have time. Okay. Before I show you how to use it, I have a few slides where I want to come back on the encoding, because I haven't maybe said much, or maybe it's a bit abstract to you. You know that on a computer, or on a hard drive, or, you know, computers only understand zeros and ones. That's the only thing they understand. That's the only thing they process. These are the bits. This is why we call it digital, right? And the idea is that if we want to store text, you know, for like JSON, XML, and so on, or binary formats, we need to encode all the information we want to store as zeros and ones. This is called an encoding. Right? So this is pretty much what we do. We encode characters. It can also be binary data as zeros and ones. So what do you need to know about text encodings, where, again, you're not computer scientists, so the main thing that you should know is that in the very ancient times of computer science, the popular format was called ASCII, and it was just, this is an old drawing, it was just 128 characters that are basically the letters, the digits, a few symbols, and so on. And that basically gives you an encoding of each one of these symbols on 8 bits. Right. So that was one of the very first standards for encoding tests, but it only had these simple characters, no accents, no other alphabets, and so on. So that was the very beginning. But things have changed now. And now you should no longer use ASCII. This is a no-go. Now you really have to use an international standard that's typically Unicode, that is the list of many characters. And then what's called UTF-8 is the encoding of these characters, like even, you know, Greek letters, Arabic, Cyrillic, Chinese, Devanagari, everything is in there in the Unicode, and then you encode that as zeros and ones. All right. Okay, so this is for text, and in the case of document stores, in that case MongoDB, as you might guess, it's not going to encode JSON as JSON. That would be very inefficient, that would be slow. So what it does instead is that it turns this JSON into bits like this in some specific format. I'm not going to explain that format. There's a standard for that somewhere. I think it's bisonspec.org is the website where they explain that. But they basically squeeze this object into something more efficient and more compact than JSON. That means that we will read it faster from the disk, right? But on the logical level, that's pretty much JSON that reads. The one thing that they did in that encoding is that normally JSON only has numbers, strings, booleans, nulls, and that's pretty much it. Well, in Bison, they did add a few types. They added the dates. For example, there's dates, there's IDs to identify objects in the document store and so on. So that's a bit a JSON++, if you want. It's a JSON with a few more data types. But that shouldn't really surprise you, because we saw that data frames do the same, right? Data frames, you also have plenty of other types. That's a very common thing to do, right? But the one thing to remember is Bison is just a binary encoding of JSON that is more efficient than if we had stored JSON as text. Now, if you think of the little elves, by the way, under the Antarctic that are storing the documents on the shelves, that's actually a perfectly valid implementation of a document store, right? In the sense of data independence, you could absolutely implement a document store in that way, right? But then you basically need to find the elves that do it, which is another story. But the reason I put this answer is really to insist that data independence allows you to implement it in any way you want. In a way, a library of the antiquity, like Alexandria and so on, was a document store, right? We basically stored the books. The books are documents, and we stored them on shelves, and that was already a document store. So we didn't have the languages that we have today, but that's pretty much it. You have the lookup, that you can look up a specific book. You can sort the books, arrange them in categories, and so on. Okay, enough about data independence. So the MongoDB stack is, as I said earlier, that we have well-formed JSON that can be valid, or you don't have to validate, as I said. But now we don't have CSV or whatever. We just have the bits in the Bison format. This is the MongoDB stack. Right? Any questions so far? Is everything clear? What's going on here? No questions? Also not in the lecture hall?
No.
All right, let's continue then. Let's start to actually look at the actual technology. That's the best start, right? Let's start querying a document store. So first, a reminder, this is not new to you. I've already told you that. When you have a database or a data store, there are two main paradigms. One of the paradigms that is very popular in big data is to have a data lake. A data lake means that you have Amazon S3, HDFS, Azure Blob Storage, and you just drop the data in your data lake, And then you just read the data from where it is, in situ. That's the Latin word for that. You read the data in situ with a massive parallel processing framework that can be Apache Spark, that can be Hadoop, MapReduce. And there, of course, you can also do it if you want with the Pandas library with Python on smaller amounts of data and so on, right? But basically, this is the paradigm where you drop your data on a data lake and then you read it from there. It's perfect for logging or pouring data without bothering to validate it. And there is this other paradigm that is the good old database paradigm where you don't just drop your data. You need to import it in the database cleanly, right? So you need to go via the proper place and import your data in a database. This is what relational database systems do. This is what PostgreSQL does, IBM, Oracle, Microsoft, they all do it that way. You import the data first. This is also called ETL, for extract, transform, load. It's actually a verb. You can actually say IETL, UETL, ETLs, SheETLs, and so on. So you basically have to import your data first. So what is new with MongoDB that differs from what we've been doing so far in the lecture is that in MongoDB, you don't drop your JSON on a data lake. No. You import it nicely into MongoDB. You also have tools for doing that. And then MongoDB is going to nicely store it on your drive in an efficient manner, and we see that it even indexes it and so on. So this is the good old way of doing database. But what's very important is really that you understand the difference between the two, right? Data lakes versus databases, data stores, right? Okay. Well, I should say database management system, not database. The database is the data itself, right? But the database management system. Okay. All right. The thing about MongoDB is that it's not as complete or as full-fledged as PostgreSQL or Microsoft, Oracle, IBM systems, right, that are complete. It's on a lower level of things, so you are closer to the actual data. The API is a bit simpler. I've already told you there are no joins. So it feels a bit more like using HBase, in terms of the level of abstraction. So you don't have a language like SQL or anything, but you have an API that you can use with JavaScript or Python. On the low level, that API allows you to create, read, update, and delete. That should a bit remind you of HBase, right? In HBase 2, you can insert a row, you can read a row, you can maybe not, you can scan. Of course, you can update data as well, and you can delete, right? But this is called the CRUD, C-R-U-D. It's just the 4 primitives that you expect to find, at least in any document store, right? Create, read, update, delete. And of course, I'm going to show you how that works. I'm going to show you concrete ways of doing all of that, but that's pretty much it. And the typical usage that people have of MongoDB or technology like that is that it's a backend for a website, right? So they use it as a database, and then it's from PHP or from whatever language you are going to call the MongoDB API to use these primitives. All right, let's go ahead and start querying things. So let's start reading. The simplest thing you can do is read everything. So you have a collection and you want to read everything in that collection. So obviously collections have a name, right? Just like the tables have a name. So let's look at a collection that's called scientists. So how do I retrieve all the documents in my collection called scientists? Well, the way I do that is that I have to write DB. It's always DB dot, then the name of my collection, DB.scientist, dot find. Right? It can either be an empty call or you can have an empty object. And we'll see that we can actually put stuff in that empty object. This is the reason why, but it's the same that we do it this way and that way, right? And when you do, you will get, if you can open a shell, by the way, just like you have a Spark shell or a Jupyter notebook or whatever, then you type that, and then you have all the JSON objects that appear and that are basically the results of your query, right? Now, a few words on that. First, this is actually the JavaScript language right there. You don't really need to care about it because the way we use it, it's just like PySpark, right? That it's Python, but actually it doesn't really matter that it's Python. Sorry about that. I didn't have time to mute, sorry. This is JavaScript. And the shell, there is a JavaScript shell, but it also exists as a Python interface, right? But don't worry, if you don't know JavaScript, it really doesn't matter. You will understand everything. One thing that I'm doing on every slide here is as a cheat sheet, just to make you understand, I'm also including a SQL version of the query if there is an equivalent. That's just so that you can see that some of the things here, we could also do them in SQL if the data were a table. But as we would see, of course, the data can be nested and heterogeneous, so it doesn't always work, right? But that should help you a bit, right? But again, it's just FYI, this is not part of MongoDB, right? Okay, and one last thing here, there is actually an extra field here that is added automatically by MongoDB called _ID. It's just some identifier to uniquely identify every object. You can consider it a primary key that is always there, right? But for simplicity, I'm just dropping it from the slides to not overcomplicate them. All right, so this is my select star from scientists. This is how it works. All right, now, of course, you can add things in that object right there and do what is called the selection. You can select the objects for which the theory field or key has the value relativity. So if you look at this collection, we'll have this first object and we have this last object. So the return is this one and that one, right? So this is a selection and that would correspond in SQL to a where clause, right? This is what it would do in SQL. Okay, then you can project. So project in SQL would be if you add the column names. How do we project? Well, it's a second parameter to my function call, find. I just say, okay, I want first. So this is why the one, this is what it means. I want it. 0 would be, I don't want it. So I want first and I want last. So here I'm just taking first and last, and that's it. And I'm dropping the rest. So you can project. Good news, right? You can select, you can project. You can also project away. That's something you cannot do in SQL. You can basically say, I want everything except theory. So you drop theory, you remove it, but I keep all of the rest. You cannot do it in SQL, but this is because in SQL you have a schema, you know the columns. In NoSQL, you don't know the schema, you don't know the columns. So this is why this is useful, right? You want to keep all the columns that you don't know, because there can be any columns, but you drop just one column. Just excuse me for 1 second, needs to sneeze again. All right, and I'm back. All right, so selection, projection, projecting away, no equivalent. We can also have the end of the where clause, right? We just have a bigger object, right? So this is a conjunctive semantic. So it's both must have theory relativity and last Einstein. So in that case, you just keep this one right there. You can have or this. Then you need to use a special key. So they use the $ in MongoDB. And then you put in an array. So you see, this is actually JSON. Your query is in JSON. Here you say last is Newton or last is Einstein, right? And then you will have Einstein and Newton. Now, this is probably the moment when you start to be a bit scared, because you might have noticed that this is kind of getting complex now, right? Compared to SQL. And basically, this is what I meant earlier when I told you, be careful, MongoDB is a lower level of abstraction. You have your hands closer to the data. So this was expected, right? And this is it. It's a lower level, it's more efficient, it's faster, but you have to learn it and make it work and so on. And that's a bit low level, right? But don't worry, because we're going to fix that next week. Because next week, I'm going to give you a language that looks more like SQL for doing the same thing as here, right? So just stay tuned for what we will do next. But before we do, I just wanted to first make you feel how difficult it is to work at that low level, right? So you fix the fact that your data is messy and nested and you want to query it, but we don't have yet a language like SQL. Right? This we still need to do. All right. So how do we compare? It's also done with the $ thing, GTE, greater than or equal. So publications here must be greater than or equal to 100. So we take this one, but not 30 and not 50. again, you see that this is less intuitive than in a language like SQL, right? But this is what it is, right? So you basically have this language where you encode your query as JSON. Now, how do we deal with heterogeneity? Because I told you, okay, we can support heterogeneity in the collection. What does that mean? Well, maybe my collection here has missing fields. For example, theory is here, 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 and here, but it's missing here. Now that couldn't happen in a SQL table, right? You would have it maybe with a null, but it would be here. But here we have a missing field, so it's heterogeneous. So what's going to happen is that it's no big deal. If we try to find theory relativity, it's going to return this, it's going to return that, and this is just going to be skipped, right? Because it doesn't have any theory, so it surely doesn't fit the query, right? That would be kind of the equivalent if you forget that it's heterogeneous. Okay, you can also try to query for a missing value using the null. So null in MongoDB is a bit special, and it's considered to also include the case that the value is missing. Do we have any questions?
No.
I heard some noise. Okay, perfect. So this is how we deal with heterogeneity. In SQL, that would be amounting to checking for null, right? You can still check for null, which is kind of a mini kind of heterogeneity you can have in relational databases. All right. Now, nestedness. So this query right here, the dots here, allows you to navigate in the key name and then the key first. So this is going to find all the objects that have name point first is Albert, name first Albert, or name first Kurt. So this is not returned, right? So you notice then that not only the dollar is important in the MongoDB language, the dot is important as well. This doesn't look for the key name dot first. It interprets the point as a nestedness. So it looks for name and then it looks for a nested first, right? And I'm going to end on that. Do not do that. If you try to mimic the structure of the JSON object and put that here, this here is going to look for an exact match. It's going to look for when exactly you have name first Albert, exactly like here, but it's not going to return that one because here you also have last Einstein that wasn't there. So that's the difference. You should really use a dot if you want to check for a nested field, and only use this structure if you want an exact match of exactly that object right there. Okay, so I'm going to stop here and just check that you understand what I've been telling you. Again, I repeat, because this is very important, MongoDB is low level. You have been warned. The language is not easy and is a bit complex, but we'll see that we'll have next week then suddenly a better language that is closer to a higher level and closer to SQL. At the exam, you will not have, well, theoretically you will, right? But you will not have practical queries with MongoDB, but you'll have practical queries with SQL, with JSON, that is the language we'll see, with Spark SQL, and with PySpark, right? But I'll come back to these details. All right, let me stop here. Let me stop scaring you with the low-level querying and just quickly check that you've been following. I just need to switch my screen. And here you go. So this is just to control my speed. All right. So you see the logic of what we are doing. In the same way that I first showed to you PySpark and Spark RDBs that were complex and low level, and then I basically freed you with Spark SQL that is much easier to use. Today, I'm showing to you the low-level way of querying nested and heterogeneous data. And next week, I will free you with a higher and easier language to do all of that, right? So it's really pedagogical so that you see all of these things and that you understand the challenges that it's actually complicated. So if you understand that this is complicated, then this is great. This is what I want. Okay. All right, so thank you very much. So this is almost a tie between 80-50, so I'll be careful with the speed. Don't worry so much, right, because we don't have much material left, actually. What's left is we'll finish MongoDB, then we'll learn JSONic and with RumbleDB, and that will pretty much be it, right, for the course. All right. Do we have a question in the chat before we go?
Do you know the date of the exam?
I don't think it's out yet. So the date of the exam is decided centrally by the examinations office, and they should send an email anytime to inform everybody that the exam dates are ready. But when they are, it's all exam at the same time, not just this exam right here. So I think you will know the exam date at the same time as I will. I will just be informed exactly at the same time as you. All right. So it's the only thing I can tell you is that it's somewhere in August. Or maybe beginning of September, I don't know, but that's basically the exam window. This is known. What I can tell you is that it's going to be a computer exam, right? With Moodle questions, a lot of multiple choice, filling text, practical exercises with PySpark, Spark SQL and data frames, SQL and JSONic, right? And the rest will just be normal questions. Is there another question in the chat?
That's exactly what you just said. The format of the
all
exam.
Right, perfect. Yeah, and we will give you past exams. There's plenty of them. So we will publish them. Then you can train. We will also give you the data sets that you will query at the exam. We'll give them to you before the exam. So even that you will have in advance. Of course, we are not going to give you the questions of the exam, right? But we'll give you the data. And that way you can even train on it and make yourself familiar with the data. Right, so now the TAs are working very hard on the exam preparation. Okay, any other questions? Otherwise, that's pretty much it for today. All right, then thank you very much, everybody. Enjoy the exercise sessions. Thank you, Wenxi, for the moderation. And I'll see you next week. So goodbye, everybody. Thank you.
There is a final question just pop up.
Yes,
Will there be a mock exam with practical exercises?
So I'm not sure what you mean with mock exam, but basically we will give you the practical exercises of the previous exam. You will have them, and we can even give you the data. So you can basically train yourself with the actual practical exercises if you want. So in that sense, you can do your own mock exam if you want in that way. Right.
And do we do the exam on our own computer at home?
No, that's on campus. That's in a big computer room at ETH. It's a totally normal exam environment with the TA supervising, limited time, and so on. Right. So it's just like an exam, except that it's on computer, not on paper. Right. The mock exam. You mean can we see the exam interface before? I don't think that ETH does that. However, the interface will be very similar to the Moodle quiz interface. It's going to be actually Moodle. What we will give you is the exact specification of the software that will be installed on the exam environment. So you can reproduce if you want. You don't have to, but you can install and reproduce on your own computer the environment. We will even give you the Jupyter Notebook contents that you will have at the exam. So basically, we are going to make it as predictable as possible and to give you as much information as possible, right? To just diminish your stress. Does it answer your question?
Yeah. Thanks.
All right, perfect. All right, wonderful. So see you next week, everybody, and enjoy your lunch. Thank you.